Let's talk about gambler's ruin. Gambler's ruin is a classic problem in probability. So the gambler's ruin is a gambler going to a casino with a probability of P winning, Q losing, and it start with I dollars. Every time you win, you get additional dollar. If you lose that dollar, lose a dollar. So bet, and then you either leave bankrupt with $0 or leave with total $n. So this can be described as a Markov chain. Each state is number of dollars, and you can go to the right with more dollar with P probability and Q probability of losing, and it will stop two absorbed states at 0 and n. So recall the formula that we have for the steady states, or for this case the state of the expected probability of absorption. So we just need to we just express them starting from state 0 to state n. So P0 equal to P0, P1 equals to P12. Go from state 1 to state 2, probability state 2, 0 or 1, 0, 0 or state 1 to state 0, probability of 0. Going forward is probability P, going backward is probability of Q. Same thing for everything, so we can generalize as this function. And and then the very end, Pn equals to Pn. Since P plus Q equals 1, we can express the left-hand side of this expression as P plus Q. We can going from do some algebra. We'll put it so that it looks in a similar format of Pi plus 1, Pi minus 1, Pi, and Q over P. So you get this expression. Then we can start from 1 to n minus 1. Then you can see this and this can cancel out. So pretty much all of them, like in that format, will cancel out and left with this and this. Essentially for any number, so Pj minus 1 P minus Pj equals Q over Pj to the j minus 1 power P naught minus P1. So for the gambler win, so P naught equals 1, P naught equal to 0, Pn equals 1. Plug it back in. We have, so pretty much this is gone, so we have this expression. So write this thing from P2. So P2 equals P1, Q over P1, so on and so forth. So you add them all together. Those cancels out. So we're left with Pj equals P1. All of them have P1. So P1, 1 plus Q over P to the first power. This can be to the 0th power until j minus 1 power. So it's just a geometric sum. And recall that geometric sum formula is this: when the P over Q equals each other, so fair chance of winning or losing, you have just a sum of ones. Otherwise, you can use the geometric sum formula, which is this. Since we remember that Pn equals 1, so we'll substitute j to 1, j to n. Then we have this expression. So we can calculate P1 equals to what? Substitute back the P1 back to, substitute P1 back to here, then we have the probability of winning is this. Similarly, for losing, we can use the symmetry pretty much. You can flip it on the other way around and calculate. It's essentially similar to winning, but you can just flip it the other way, go the other direction with different probability, which is kind of intuitive. You just go, so the distance become n-1, and then the rate of the odd goes the other way around, so it's P over Q instead of Q over P. And it's very, you can verify this using Martingale's method as well through the with even equal odd, like winning or losing is half and half. This is exactly what you would expect for the Martingale process.